Welcome back. Today, we're going to practice a little bit more with the so-called particle hole formalism. We're going to remind ourselves about some of the things which we derived yesterday. And then we're going to look at examples. And many of these examples are things which will serve us well next week when we start looking at the first real many-body methods, which is called full configuration interaction theory, which essentially means, if you now are familiar with things like a Hamiltonian matrix, you can rewrite a Schrödinger problem or a Dirac problem or any type of quantum mechanical many-body problem in terms of an eigenvalue problem. And that means that you have to diagonalize a matrix. Now, all the ingredients which we are going to develop today are ingredients which we will need in order to set up this Hamiltonian matrix. Now, since we are going to deal with many-body states, it means also that if we were to calculate these different ingredients by first quantization, by just setting up all the possible permutations of Slater determinants and so on, this could easily become pretty unwieldy. Now you have a very straightforward way with the particle hole formalism to actually calculate these matrix elements. Then towards the end, we're going to look at some other examples, and then we're also going to look at the diagrammatic expansion. At the end of the lecture slides, you will find also a way to represent the creation and annihilation operators in terms of Pauli matrices. This is normally called a Jordan-Wigner transformation. We will probably not go through that in the lecture today, but if we get time towards the end of the semester when we're going to talk about quantum computing, this is the way you're actually going to rewrite your creation and annihilation operators in terms of Pauli matrices. And then based on these, you can then construct operations on so-called qubits. So you will see at the end of the semester how we can rewrite this Hamiltonian, which we have now in one-body and two-body Hamiltonian, how we can actually rewrite that in terms of Pauli matrices, and then really tailor it for applications to quantum computers. Okay, so let's quickly remind ourselves a little bit about the different ingredients which we went through yesterday. So there are several things which we discussed. So one is the set of commutation and anti-commutation rules. So what we did was to define creation and annihilation operators with respect to a new vacuum. So we defined this new vacuum, and since we are dealing with fermions, these are going to be determinants, and they are based on the single particle states. This is not the exact wave function. So we define that as a C, which is often used as a core if you're doing atomic physics or nuclear physics, or we would simply label it as a phi 0, which is our ansatz for the ground state of the system. So just keep in mind that H multiplied with this ansatz is not equal to an eigenstate multiplied with this ansatz. So before we move on a little bit, let's put down some smaller technicalities here. So one of the things which we did yesterday was to redefine the creation and annihilation operators with respect to this Fermi level. So what we did then was to define a creation operator B alpha dagger, which was given in terms of the traditional operator. And this was given in case alpha was larger than the Fermi level. And then we had an A alpha, the annihilation operator, in case alpha was below the Fermi level. And then we had the annihilation operator, which now was defined as a regular annihilation operator for particle states. So this alpha is larger than F. And then we had an A alpha dagger when alpha is less than F. Now, this allowed us to actually perform the same type of operations as we had before. And the only contraction then, which is non-zero, was this contraction here, which is the same as we had before, except that now we have redefined things with respect to a new vacuum. Then, with these operators, we could actually rewrite, for example, the one-body operator in terms of this creation and annihilation operators. And what we did then was to simply rewrite it, and we got something like this. So we had the one-body operator for the energy, but this would apply to any type of one-body operator. And we could write this in terms of a double sum alpha beta for states larger than F. And then we had an alpha expectation value of this term beta, actually not expectation value, but a transition matrix. And then we had the B of alpha dagger of B beta, like this. So this looks like what we had before. But then we got additional terms. And then we had an alpha larger than F. And then we had a beta less than F. And this is something which we rewrote in terms of an alpha, matrix element of beta. And then we had two creation operators, one for a particle state and one for a whole state. So we actually create a particle and we create a whole. Plus beta of H alpha of beta B of beta alpha. So that was one term there. Then we got a new term because we want to reorder all the operators as normal ordered operators. So when you set up a quantum mechanical operator in second quantization, you always want to order them so that you have annihilation operators to the right, so that when they act on a vacuum state, you just get 0, and creation operators to the left. So we got a term here which went like beta H0 of alpha, and then we had the annihilation and creation operators for whole states. In addition, we had a constant term, which is actually nothing but the term which would come from the expectation value of the ground state ansatz to the ground state ansatz. So this would be the new vacuum expectation value. So when you had a true vacuum, just plain emptiness, then you just had 0 here. But now you get a constant term, which in our case simply runs over all the states below the Fermi level. And this is given by H0 alpha. And if the alphas are eigenstates, as we said yesterday, it's pretty common to assume that the alphas are eigenstates. So let me put hats on things as well. So sometimes if I forget to put hats on operators, I mean, it's just simply because I'm forgetting. There's nothing more mystical than that. And this is given by an epsilon alpha of alpha. So in many cases, that is a typical basis which we may choose. When we are running a Hartree-Fock calculation, this is no longer the case. However, or it may not longer be the case. So we have to be a little bit careful when we do that. But the thing is that this is something which we normally know how to evaluate. And this just gives a constant term. Now, if you look at this expression here, what we did yesterday was actually to rewrite that in terms of the traditional or the creation and annihilation operators we started with. But then what we did was to say that states below the Fermi level are labeled as Ij, Kl, and then states above the Fermi level are labeled as A, B, C, D. And since we are mainly going to deal with our up to 3 body interactions, it means that we won't need typically more than 6 letters. But if we need more letters, we will typically have an A1, A2, A3, and so on. And you will see that a little bit later today. Then,
on literature to use the general indexes?
No, this is something which is normally used in quantum chemistry.
Yeah.
So that's, you will typically see this kind of lettering. And this is a kind of lettering which has been common in some many-body methods. In other cases, people will just keep the alpha and betas, but as long as you're consequent and you know what that means. And that is the most important thing, so that you have a specific convention for the states. And then what we also defined are general state P, Q, R, S, etc. These are just a general single particle state. So I'm just going to repeat some of the things which we did yesterday, because I wanted to have everybody with me on that. Now, this allowed us to then introduce a new anti-commutation relation, where we now have a commutator or contraction, which is non-zero. So this is equal to a delta ij, or if we make it more general, we would have an AP, a general state, AQ. This is delta PQ if P and Q are below the Fermi level. So when we did calculations with a true vacuum, this contraction was equal to zero by definition, because when you act with an annihilation operator on the true vacuum, you should get zero. But now you're acting on a modified vacuum state, which is your reference state, and then this state Q may actually be occupied. And then the action of AQ on the Slater determinant you have may not be zero. And yesterday we also defined the other contraction in case we have states above the Fermi level. So this is equal to delta PQ. And these are the only non-zero contractions now of PQ larger than F. This gave us the possibility to define specific states. So one of the states we defined yesterday was a state which is a particle subtracted, or one whole state, or just an n-1 particle state. And that's something which now is given by A of I acting on our vacuum state, in the new vacuum state. And this is non-zero if I is now an element in this state phi 0. Because then we know that we are removing a particle. So this is an n-1 state. And then we also introduced a state with a label A. So A is now a state above the Fermi level. And in that case, this was given by the creation operator acting on your vacuum state. And this is something which now is obviously, so A is not in phi 0 by definition, because that's a state which we have explicitly defined to be outside the occupied states. This becomes an n+1 state. And then we define what we call the one particle, one whole state. And in that case, we would have a state which we label like a phi A of A. And this is now given by an A dagger A of I acting on phi 0. So this is an example of a one particle, one whole state. And the whole thing is now that we are going to replace the way we think, which we normally have in first quantization, where we let the particles interact an infinity of times. Now we're going to let the particles interact through an infinity of one particle, one or particle hole excitations. So we could define a two particle, two hole excitation. And this is something which we can define as an Aij and AB here. So when you see something like this, then we would have the operation of two creation operators for particles, and then we are removing a hole. And then we have a J, because we want this to be anti-symmetrized. And this is times phi 0. If we were to use these operators, B, this would be the same as a B of BB. And then I would have B of J, dagger, and B of I, because we're creating a hole. So if you want to use these operators. Now, keep in mind, there's one important thing which we discussed a lot yesterday. When we did this transformation of the operator, what you see here is that this rewriting, because we want to have the operators normal ordered, that brings in a minus sign. And that's important now when we are looking at the contractions, and later when we are going to look at a diagrammatic representation. Because when two whole lines contract, that's going to give rise to a minus sign. And you can see that minus sign explicitly in the expression here for the one body operator. Okay, so you can go on like this, and you can have a free particle, free hole state, etc. But you could also have an n particle, n hole state. So if you have n particles, and that means that you can actually, which you are distributing among all the states, then you can actually create an n particle, n hole excitation. And in that case, what we are going to do then is to use a slightly different labeling. So we will have I1, I2, and then you see now that a notation. So this is up to the number of whole states you have. And then you would have an A1, A2, up to the number of states. And now we're going to put an N here just to indicate that these are the states with N particles, which are filling in. And that means that you would have an A of A1 dagger, A of A2 dagger, up to A of AN dagger, and then you have an A of IN, and this goes all the way down to A of I1, acting on your vacuum state of phi 0. Now, the reason why I introduce this is that I'm going to define a more general notation for this. So I'm going to call a general particle hole excitation. I'm going to use this notation here. And the reason why I do this now is that because I want to link what we are going to do today with what comes next week. So I'm going to use the general notation for a particle hole state, for a general particle hole state. And I'm not specifying whether this is a one particle, one hole, two particle, two hole, or whatever. Two particle hole state. This is something which I will simply label as a phi of H of P. And you can put in as many as you want. Now, this is just a way to rewrite your total set of basis states or your computational basis. So remember now that we have a set of single particle states. In principle, this is an infinite set of single particle states. And we are filling this up to the Fermi level. So we have filled in slots here. So this is normally what we call for this vacuum or new reference state, phi 0. But then if we have n particles, and we have n little n and n slots. So every single particle state, you can think of that as a slot, which then in every single particle state, that points to specific quantum numbers. And they are unique since these are fermions for that given single particle state. And then what we found is that the number of Slater determinants or number of configurations, which is a better word, the way we can distribute these single particles, these particles in these single particle states, is then given by the binomial factor of n and uppercase letter n. And this factor is simply given by n factorial of n minus n. And we are assuming now that the little n is larger than the uppercase n. So the assumption here is that n is larger or equal to n. So that means that when we are now ordering all the different Slater determinants we have, you could now think of these ordered in a specific way, which you decide. So what we are doing now is simply to order all these configurations in terms of particle hole excitations. So order the configurations in terms of particle hole excitations of P, and I'm writing this generically, pH excitations. So this is just a bookkeeping, but it's going to be a convenient bookkeeping because you can think of this bookkeeping in physical terms. So if the basis you have when you construct your many-body basis is a basis which is pretty close to, let's say, the exact solution for the ground state, then you filling in the state phi 0 with that single particle basis makes what you might call a meaningful approximation to the state function. If not, it's just a handy computational basis, because you would, in principle, since you have little n goes to infinity, you have an infinite set of such configurations. So we are simply reordering everything in terms of particle hole excitation. So we will have 0 particle and 0 hole. And normally we assume that the ground state is not degenerate, but that happens if you're looking at systems like the the lithium atom, and you think of the lithium atom, which has one valence electron in the 2s orbital. It can have spin up and spin down, but the Hamiltonian doesn't act on spin. So this is a degenerate state in that representation. But we are going basically to assume that the ground state is non-degenerate, that there is a unique representation of it. But then we would have, in principle, an infinity of one particle, one hole states. So these are the states which we simply label as A of I, like this. And then this just goes on, two particle, two hole, etc., etc. And this is an orthonormal basis. So the assumption we have made now is that if we now take the inner product of an H prime and a P prime, or phi of P of H, this is given by a delta P of P prime and a delta of H prime. And yesterday we also saw typical examples of that. Now, why is this important? Now, this is important, this kind of reordering is important because what we are going to do now is to rewrite the basic wave function which we have. So suppose now we have the ground state of the system, the true ground state. Since this is an orthogonal basis, we can expand this one in terms of the basis set which we have. So in principle, what we have, if we look at the Slater determinants, the way we wrote it earlier is that we would have a sum here, and then we have a unitary transformation, since we are dealing with complex objects, and we are assuming that the problem is Hermitian. So there will be a J0 multiplied with this original basis of Slater determinant, where we have not made any reference to a specific ordering. Now, we are going to rewrite this now in terms of the sum of all the particle hole configurations which we can make. So this J becomes now simply the set of particle hole configurations. So it's just a reordering. So you're free to reorder things as you want. So that means that now I'm just going to rewrite as a new coefficient. So I'm just going to call this CHP. And this is now given in terms of this new basis here of P. So when you act with the Hamiltonian, then what you're going to need in order to set up this Hamiltonian matrix, we are actually going to need matrix elements of the type where we now have a phi H prime of P prime. And then we would then have the Hamiltonian, which acts on the system. And we would have, on the bra side, we would have another particle hole state. It could be a zero particle hole state if we want to. So these are the matrix elements we need. So these are needed when we now are going to move over to our first real many-body method. Now, one more thing before we look at examples, because it's useful to now actually run through some of these examples and see how we can calculate them efficiently using the normal ordered Hamiltonian and Wick's theorem. So what we did yesterday with a two-body Hamiltonian, we ended up with the following normal ordered rewriting of the Hamiltonian. So let's set up the equations which we are going to need in order to calculate these matrix elements. So we defined the Hamiltonian in terms of a constant, which is the reference energy. That is the vacuum-to-vacuum expectation value. So this quantity here, when we now go to this quantity which we put up here, that is the same as phi 0 of H phi 0. And this is something which we normally would subtract from the total energy, and then we are simply interested in the contribution from the other states. And you will see clearly next week when we are looking at many-body methods like configuration interaction theory in specific fields like in atomic physics and in nuclear physics. It's often called a shell model. In nuclear physics, called the nuclear shell model or just a shell model, because the single particle states you defined for the system, they are related to an experimental indication that there is a shell structure. So atoms and nuclei exhibit a shell structure, and you will often encounter what's normally called, or formally called, full configuration interaction theory, where you set up all configurations as the, let's say, the nuclear shell model or the atomic physics shell model. So sometimes I'm gonna use this interchangeably. Then we got a term which we call for F, which is the one-body operator. And this term is given in terms of normal ordered operators with respect to the new vacuum. And if you go to the textbook by Shavit and Bartlett, they would put an N under it here to indicate that this is normal order with respect to the vacuum, but I'm not going to use that. So I'm just going to write F here. And then we had a two-body term, which was the two-body interaction. So let's rewrite these terms. So the first terms follows from what we just reminded you of when we introduced the other operators. So this would be just a generic sum of PQ. And then I have a matrix element of P. And I have this operator F now. And Q. And then I had this normal ordered operator with respect to the new vacuum. And later we are just going to drop these curly brackets here. This operator F has a matrix element which has a P of H0 with Q. And that piece is the one we've seen before. And for this specific case, when we are calculating this term, I mean, in case these are states below the Fermi level, this will actually be something which would enter this reference energy. And then we have a sum over states below the Fermi level. And this is a contribution from the two-body interaction. But then rewritten in terms of a one-body operator. So we have a P of J, and then we have the two-body operator, and then we have a Q of J. And this is an anti-symmetrized matrix element. So just let me quickly remind you of these operators PJ, or these matrix elements PJ and QJ, anti-symmetrized, that contains the direct term QJ minus the exchange term. And we normally lump them together because then it's more handy to tabulate just one instead of two matrix elements. So the second one is what we normally call the exchange matrix element. So this is the one-body part of the operator. And then the two-body part, this V, is then given by 1/4. And then we had a term which simply runs over all the all the single particle states, all the four, and S. And then we have a matrix element, P of Q of V. You can use the standard matrix elements which are not anti-symmetrized. Then you would have a factor of 1/2. Anti-symmetrized, and this is then multiplied with AP dagger, AQ, AS, AR. Now, in many textbooks, you will often see that people drop this AS symbol, and then you have to deduce from the context whether they are defining anti-symmetrized matrix elements or not, because if it's not, then you have a factor of 1/2. If you see a factor of 1/4, it's an anti-symmetrized matrix element, as we derived, I think, 2 weeks ago. So these matrix elements here have a specific symmetry as well. So this is equal to JP of V of JQ, anti-symmetrized. And if I interchange one of them, this is actually, this anti-symmetrized matrix element is actually equal to minus PJ of V of JQ, anti-symmetrized. And it's easy to convince yourself that these kind of symmetries pertain to these kind of matrix elements. Okay, so one of the things we did yesterday was actually to calculate some of these expectation values and transition matrix elements. So one of the quantities which we looked at yesterday was the calculation of phi of I, of A, of H, of phi. So this is what we would call the diagonal matrix element. And in that specific case, what we found was that this was equal, and it has a pretty simple matrix element. This was equal to the matrix element of I of this quantity F of A. And the thing we're going to do now is actually to calculate more of these matrix elements. If we then looked at the matrix elements of, oh, sorry, wait, I think I was actually reading I was reading the wrong line here. Sorry, let me just remind you of the type of contributions which you get. So let me redo everything here so that we have everybody on the same page. I was actually looking at the wrong line in my notes here. So what we have when we are setting this up is something like this. So we would have a C, and then we have a state AI dagger, A, and then we have the different operators. So let's write out the contributions which we have. So it's going to have a constant term, E0 ref. We're going to have the one body operator, which is a PQ, and then we have these matrix elements of P, of F, of Q, and then and now I'm going to drop this kind of special normal ordered sign, plus, and then I have 1 divided by 4. I have the two body matrix elements, P, Q, V, RS, and then I have P, Q, RS, and then I have A, P dagger, AQ, AS, AR, and this is then multiplied with the other state here, AI of C.
There, right?
Yeah. So let's just repeat these calculations here. Let's now look at the first term. So the first term is just a constant. So we can just write it out. So we have C, and then we have AI dagger A, and then we have A dagger AI, and this multiplied with C, and then we have just a constant E ref. So in this particular case, the only contractions which we can have, which are non-zero, are given by these. Now, this is a case where we can read off immediately. We know that I is a state below the Fermi level, so we cannot contract I with A, so that doesn't work. And that also means that we have the only possibility we have now is A with A and I with I. And when we have states below the Fermi level, the only contraction which is non-zero is the one where we have the annihilation operator to the left here, not to the right, and the creation to the left. Just let me quickly remind you of that. So when we now have defined these new operations, when we have C and we have AI of A, I acting on C, and I is now assumed to be included in C. So that's an assumption we make from now on. Then clearly this removes a state with C, and this creates one with C. So what we're ending up with is that we get this Slater determinant we call phi of I, where we have a whole state. In this case here, this is just the overlap with phi of I with a whole state here. And these states are defined to be orthogonal, and this case here is just then equal to 1. So this quantity which you see here is now something which we define as a contraction. And with a new vacuum, this is non-zero. With a true vacuum, this was exactly equal to 0. So let's look at the second term. So the second term, so we have, let me just put parentheses here just to show that this is an intermediate calculation. So the second term has now a sum over PQ. I have these matrix elements, P of F, of Q, And then I have this vacuum state now. So let's just write it like this, times. And then we have a C, and then an A, I dagger, AA. I have my AP and AQ dagger. And then I have an A and AI. And this is acting on the vacuum state. So let's go carefully through the different types of contractions we have. So if you scroll up a little bit, just to remind you of what we defined yesterday. So we have these as the only contractions, which are non-zero. These are the only ones. So this one and that one. And the labels which we have put on the different states, they are now fixed. So we are picking a specific Slater determinant with fixed single particle states. So that's why we have this labeling the phi of I and A. So when we now start looking at the type of contractions we can obviously make this contraction. That gives us a delta Q of A. And then I can make this contraction here. This is also non-zero. And remember also that what we have in principle are chains of normal ordered operators, and they can only connect to other chains of normal ordered operators. So we cannot have an internal contraction inside a normal ordered operator. So that means that for the state I, which we have here, then the only contraction here which is valid is this one. So that gives us a delta of P of A. Now, if I were to try to, let's say, take this contraction, that's obviously zero by definition. If I take this one with that one, that is zero, and so on. So I'm only looking at the cases which are non-zero. Then I have another contraction which I can make. So I can now perform the contraction with AI with AQ. So that's a viable contraction, delta IQ. So Q becomes a state below the Fermi level. Now what happens now is that I cannot perform a contraction with, obviously with A to this state. That's obviously zero. I cannot perform, so I haven't dealt with P. I cannot do that one with this one because that would also be zero. So for the two particle operators, the AA and the AA dagger, now the only contraction is actually this one. Then what you see now is that I have contracted AI with AQ, but then the only other one is actually AP with AI. Now, since we now have crossing lines here, you remember that that means that we have to interchange operators, and an interchange of operator gives a minus sign. So this gives us now delta I of P. So an intermediate step here, just an aside. So the first element gives us now A of F with A. And the second one gives us minus I of F with I. When I look at the matrix and take the Kronecker deltas. And then this has a delta II multiplied with it. And this has a delta AA multiplied with it. Then if we open this up, if we just write it out in detail and we skip the Kronecker deltas, this is going to contain A of H0 of A. So if A is an eigenstate of H0, this is just a constant. If we assume that, this becomes epsilon A. But then we have a new term. And the way we're going to interpret this term is actually interesting. So this now contains A with a J of V of AJ, and this is an anti-symmetrized matrix element. So what is happening here now if you think of this as a one-body contribution. So in the previous case, you have an external field, which is given by H0, or it could just be kinetic energy. So if you think of an external field, this is actually something which in some cases is artificial. In nuclear physics, it is, because many people use the harmonic oscillator, but there is no harmonic oscillator in nuclear physics. But it fits because it's a good ansatz for the lowest lying states. However, nuclear physics has kinetic energy plus nuclear force. If you do atomic physics, this H0 could contain the attraction from the atomic nucleus due to the Coulomb interaction. And then you would let the repulsion between the two electrons be represented by the term V. So in some cases, there is a natural external field, and in other cases, this is just a theoretical construction, because you want to have a handy basis, which is diagonal for these operators H0. So keep this in mind. There is nothing like nature does not need to look like the basis which you have chosen. So in many cases, we choose a basis because we have analytical solutions, and that makes it handy to calculate many matrix elements. But it's not given that the exact, somebody gave you the exact wave function. It may not look like your ansatz. So your ansatz is physically motivated, but also practically motivated. So what happens now is that you can think of this. So if you think of this particle in the state A, it sees its kinetic energy, it sees an external potential, but then its movement gets changed by the interaction with all the other particles below the Fermi level. So this is something we are coming back to when we are going to discuss Hartree-Fock theory, because what you see here now, this operator F enters the definition of Hartree-Fock theory. And it's a simple many-body theory where you can redefine a complicated many-body problem in terms of coupled single particle equations. So that's essentially Hartree-Fock theory. Okay, so that was this, but then we have minus, and then we have an I, an H0 of I minus, and then we have this sum J, and then we have Ij, V, Ij of AS. So that's what we get from that. Finally, we have the two-body piece. And let's set up that before we take a small break. So we have a PQRS, and we have PQ of VRS. And as I said, I'm skipping these curly brackets to indicate that we have a creation and annihilation operators, which are set up according to the new vacuum. So we would have an AI dagger AA, and this is multiplied with AP, AQ, and then AS, AR, multiplied with A dagger of AI of C. Now, this second term is actually 0. And the reason for that is that we are going to have up two sets of operators in the expression for the Hamiltonian, which are not going to be contracted with any of these particle states, which defined in the Slater determinants. But we're going to see that after a small break. So I'm going to put the recording on pause here, and then we take just a small break here and stretch legs a little bit. And probably you also have questions. What we want to do now is to try to wrap up the calculation of this specific contribution to an expectation value. So this is going to be a diagonal matrix element because we're going from the same Slater determinant to the same Slater determinant. So the thing we need to look at, the final piece, is the term which now involves the two-body interaction in normal ordered form. So let's look at the possible contractions which we can have here. And again, we are going to use Wick's generalized theorem because we have strings of operators which are normal ordered. So if we look now at the operator itself, suppose now that we take this annihilation operator in the operator, and then we contract it with the only possibility to the right. So it cannot contract with the whole operator here, the annihilation operator, because that's automatically 0. So when we look at these operators which you have here, these ones, they can contract with that one. Now, these operators here, they can obviously talk to this one. And then if we look at these guys here, they can obviously, this one can be contracted with this one or that one or this one. And that gives something which is non-zero. And similarly, this one can be contracted with these two operators or that operators. So this A dagger here can then operate on 3 of the operators to the right of it. So let's just now look at one specific contraction. Now what we said now is that so this A of I could in principle go over to A of, if you look at this one, it could actually be contracted with that one, or it could be contracted with this one. These are the only possibilities now, since we have blocked this A of R here. So let's look at this possibility here. Now then, what we have is that we have A of A. So A of A could now actually go to AP or AQ. So let's now assume that it goes to AP, one of these. Then what happens, as you can see here, is that we are left with 2 operators within the same normal ordered chain of operators. And that is automatically 0 by definition. So that's 0. Now what I could do, I could change this one to that one, but then I would have AP with AS. Alternatively, I could now take AS to A of A, but I would still run into the same problems. I would actually always be left with a possibility where I have a contraction within the same chain of normal order operators. So this contribution here is going to be exactly equal to 0 when you go through all these different types of contractions.
Is there a way of seeing that beforehand? Or
no, you have to go through it. You have to look at it. But you could have, with some experience, you know that when you have a state like this on this side and that side, and then you know that you have only this type of operators here, then you could have said that there will be a set of contractions which will take place within the same chain of operators. But that's something you build up with some experience. Yeah. So the term which comes from the 2-body interaction is equal to 0. So we are only left with these 2 guys here and the reference energy, which we put up in the very beginning, which we had up here. So if we summarize that matrix element, we would then get summary. So all these, we just put 0 here. So you get E0 ref plus these matrix elements with the for the particle state with this operator A minus I of F of I. Now we're going to look at more examples, and it's useful to actually do this. And I'm going to give you this kind of exercise for the weekend, just to keep you busy in the weekend. No, just joking. There are several of these matrix elements which we need when we are going to set up what's normally called FCI, or full configuration interaction theory, next week. So one other matrix element which we are going to encounter many times is actually this one between the ground state and one of these states. So this specific state here, or this specific matrix elements which we're going to look at, is also pretty simple to calculate. So if we now look at the first term, which is just the reference piece, so that's a constant which we can put outside. So that's simply going to have AI dagger, AI, AA dagger, and AI multiply 0. And we see this is automatically 0. So this contraction here is not possible because A is different from I. So this term is 0 by definition. Then we have the next term, which now includes the one-body operator. So we have a sum over PQ, and now we have a P of this operator F of Q, And then we have the vacuum state, and then I have my AP dagger, AQ, and then I have my A and AI here. So that's the next term. Now, in this specific case, we see now that we can have contractions of this specific type. That's fully possible. That gives me delta Q of A, and I can have this contraction. And that gives me delta P of I. If I try to contract AP with AA, that's 0. If I do AQ with AI, that's 0. So this is actually the only term which contributes. So what I get here, and let's put this in parentheses, this gives me now I of F of A. And this is the same as I of H0 of A plus this specific contribution here, where the different states actually see a contribution from the vacuum state. So that can be seen as a correction to the motion of these given single particle states. Now, there's an interesting thing here, which I'm going to mention. When you do Hartree-Fock theory is a reduction of the many-body problem to sets of coupled one-particle equations. And what happens in Hartree-Fock theory is that these matrix elements are set to 0. And that's an interesting thing. And we are coming back to that. In the basic Hartree-Fock, these matrix elements, when you solve the coupled single particle equations, you're going to find that these matrix elements are 0. So it's a kind of, if you think of this as a big Hamiltonian matrix, is a kind of unitary transformation where you zero out blocks of matrix elements. And we are going to see that more clearly next week when we start with our first many-body method. So that's the next, and then we have the final contribution where we have to take into account this term here. And then we have PQ and R and S. We have the matrix element PQ, V, R, and S. And now we have to look at the different contractions. So now we have an AP dagger, AQ, dagger, AS, AR, AA dagger, AI of C. And now you see again that you're going to have two operators which will not be contracted except for being contracted within the same string of normal order operators. So if you look at the possible contractions you have, you can now say, okay, I can do this contraction. This is non-zero. And then I could take either AP or AQ and contract that with that one. So if I take one of these, suppose I do that, that's also viable. But this final one, that is equal to 0. So if you now start looking at what you have here, you will see that all these terms will always have a contraction where you have operators within the same normal ordered string of operators. So the final term here with the two-body interaction is going to be 0. So the only contribution which you have is also the one which we found when we calculated this in the second exercise set. We actually calculated these matrix elements. And what you end up with then is simply this contribution here. So it's a pretty powerful method when you use second quantization and then you have redefined the vacuum state. Then another matrix element which we will need is actually this one with a two-particle, two-hole excitation. So let's take a closer look at that one. So in the first case, we have a reference energy term, EREF. And that means that we would have matrix element C, and then I would have an A dagger, AB, and AJ, AI of C. And we see that that's immediately equal to 0 because A and B's above the Fermi level, J and I are below. and these are distinct states and they're different. So there is no way that we can have any contractions here which are zero, which are non-zero. So we would have a delta A of delta I multiplied with delta B and delta J. And this is by definition of the single particle states we have plugged in, this is automatically zero. So this doesn't give any contribution. Then we have the next term, which is now the one body term, PQ, and then I have my P, the operator F of Q, and now I have my state C, but now I have the operator AP, AQ here, and then I have my AA dagger, AB, and AJ, AI, and C here. Now, in this case, what we see again is that I can have a contraction of this type, that is non-zero, if I take the operator, and then I could have a contraction like this, which is also non-zero. So this would be give me a delta Q of A, and this would be a delta P of J. But then I now have to contract AB here with AI. And that's automatically zero because that requires a delta B of I. And B is a particle state and I is a whole state. So that is not possible. So you see now that if you keep doing this, what you're going to see then is actually something which now is going to give automatically zero contribution from that specific term. So the one body operator gives us automatically zero because we will always end up with a contraction of a particle state with a whole state, whichever way we reorganize this. And it's easy to see if you now set up all the contractions that this is actually going to happen. So this second term, the one which comes from the one body operators, is zero. So let's now look at and I invite you to take a look at that and just write out all the possible contractions. But now, even if we haven't gone through all the contractions, we are going to do that in the last piece here. So we have P of Q here and RS. So this is the two-body term. So there's a matrix element PQ, V, RS, anti-symmetrized. And now I'm going to rewrite everything here. So I'm going to have a C with an AP dagger and then AQ dagger. And then I have an AS, AR, and then I have my AA, AB of AJ of AI with C. So let's go carefully through this now. And let's just start picking terms. So we can have this contraction is non-zero. This contraction here is non-zero. Then I can have this contraction here, which is non-zero. And this is also non-zero. So if I collect terms now from this one, I'm going to get a delta P of I. I'm going to get a delta Q of J. So I and J are whole states, or states below the Fermi level. And then I get a delta R of A, and I get a delta S of B. So when I bring everything together, this term is going to give me a matrix element, which I just write below here. So it's going to be IJ, V, AB, anti-symmetrized. And this is a factor of 1/4. So I'm just leaving that outside here. So that's the first type of contraction, which gives us something which is non-zero. So let's now move to the next one. So what I'm going to do now is to keep the particle states. So remember now this AR cannot go to any of these. Same with this one, because that's automatically zero. These here cannot go to these because that's automatically zero. we cannot do contractions within the same operator. So let's now look at what we have here. So let's keep this ordering for the particle states, but now we can interchange. So what we would do now is to let P, instead of going to J, we let P go to I. And then we take Q, and in that case is, let me see now. Now this, I actually had, I had that one. So it should go to J here, sorry. So P goes now to J. And now I'm going to get a crossing line here. So this is going to give rise to a minus sign. So in this case, I have the same. I have a delta P of I, a delta Q of J, and then I have a delta R of B, and I have a delta of S of A. So that's going to give me a matrix element now, which goes like J I V A B, anti-symmetrized. But since we're crossing a line here, so that means that we have to interchange one, we have an odd number of interchanges of operators. That gives me a minus. However, this matrix element, since it's an anti-symmetrized matrix element, this is equal to IJ V AB anti-symmetrized. So I have two terms. So let's continue. So now we put in a new color here. So let's now look at the next possibility. So let's keep these two whole lines as they were. But now we interchange the two particle lines. So what I'm going to do now is to do this one. So what I'm going to have now is that A goes to R. And then I let B go to S. And then I'm going to get a term which goes like delta P of I, delta Q of J, and I'm going to have a delta R of A and delta S of A. Say it again.
The last two deltas.
Oh, sorry. This is me who actually broke.
Right?
That should be a B. Sorry. This is B. So that gives us a matrix element. So I have two crossing lines, minus, minus. So that's going to give me a matrix element, which is given by Ji of V of BA. But that's again the same as IJ of V of AB, anti-symmetrized. So my final contraction now, when I set everything up, is the following. So I'm going to keep the two particle states as in the previous case. So I'm going to get this contraction. So that's going to give me a delta R of A and a delta S of B. But then I'm actually going to bring back the whole state to this one. And then I'm going to have this one, which goes to that one. So this is going to be a delta P of I and a delta P of J here. A delta Q of J. So when I collect everything, this is going to be a matrix element now, which goes like minus IJ of V of BA, anti-symmetrized. And this is the same as IJ of V of AB, anti-symmetrized. And these are the only matrix elements which actually contribute, which are non-zero. So when I collect everything, this is simply going to give me the following contribution. Phi 0 of H goes to phi IJ AB is simply going to be given by this matrix element, anti-symmetrized. Now we can go, we're going to have some of these as exercises, but there are some matrix elements which we can actually now see will be automatically zero. So if I now look at a matrix element like phi 0, and then I take H, and I take a state which is now I, J, K, and A, B, C, a free body state. So this is going to be given by, I'm going to have a phi 0 with a reference state, E0 ref, and then I just put the constant outside. So I'm going to have a operator which goes like A of A of B, A of C, and then I have a AK, AJ, AI acting on this phi 0 or the vacuum state, multiplied with E0 ref. And we see this is automatically 0 because this is another state, so this has to be 0. If we look at the one body piece, so let's write this in a more schematic way, so we don't need to carry with us all the constants. So when you've done this, sometimes you get a little bit lazy, and then you simply set up the states here. So the next one would be AP, AQ, and then I would have the state AA, AB, AC, and AK, AJ, AI, and phi 0. And what you're going to see in this case is that the operator here, since we have this generalized Wick's theorem, the operator here can at most take one of these, and then we are left with 2 creation and 2 annihilation operators, which cannot be contracted with, which actually give 0, because if I take this one with that one, that's 0. That one with that one, 0, and so on. So this term is immediately 0. So you can see that very quickly. So when you want to have something which is non-zero, and this is the important thing, if you look at the operators you're trying to contract and you use Wick's generalized theorem, if they don't have the same number of creation and annihilation operators, then you will have operators which have to be contracted within the string of operators, of normal operators, and that gives automatically 0. And you see that immediately here because this state here, C, is a particle state, and you're contracting that with a whole state, and they're different by definition, so that's 0. This is automatically 0. So you can do a contraction like this, and this with that one, but you would be left with contractions when you look at the contraction, which are 0, automatically. So this means also that when you take the two-body operator, you would have an AP, AQ, AS, AR, and then you have this string of operators, AB, AC dagger, AK, AJ, AI. And now you see that you also have a different number of creation and annihilation operators here and here. That means that when you contract these with, let's say, these two and these two, which are the only non-zeros, you would be left with these two guys here, which give you automatically 0. So this term is also 0. And that's where it stops. So as long as you have a two-body operator and you have a free body state, which links with a state with 0, no, a free particle, free hole excitation, which links with a state with 0 particle, 0 hole excitations, this is automatically 0. So the only way you could have something which gives a non-zero contribution would now be that this state here would have to be something like a phi of I of A. Because then you would get a particle hole pair, which comes in. And that means that you would actually have phi 0, and then A, I dagger, A. And then suddenly you have an equal amount of creation and annihilation operators in all the strings.
So we know which terms are not.
Yeah, so they are non-zero. But if you now have a more than 2 particle, 2 hole excitations of difference between the states you're looking at, this is what we called in exercise set number 2, the Condensed-Slater phase rule, or the Condensed-Slater rule, which simply says that if you had Slater determinants which differed by more than 2 single particle states, then the matrix element was immediately 0. And this is what you can see here immediately by using Wick's generalized theorem. So that's a very powerful way of actually calculating the same expectation values which you did in exercise set number 2. So we can go on like this. So we would also need matrix elements of the type, and I'm going to leave that as a kind of a small exercise. We can actually run through this one. Let's take this as a final example today. So suppose now we have 2 different Slater determinants here. And they would now be 2 Slater determinants as a 1 particle, 1 hole case. And let's just run through the calculation of that as a final example. And then if you go into the textbook by Shavit and Bartlett, you will also find many other examples. And there is a special case, which I'm going to give us a small exercise, which we also need to look at. But as a rule of thumb, what you can see now is that if you have an operator which has only up to 2 body interactions, and your states differ by more than 2 single particle states, then this gives automatically 0 contribution. And that means that when we are going to set up this Hamiltonian matrix next week, the Hamiltonian matrix is going to be a sparse matrix. And it will have only some few matrix elements which are non-zero. Okay, so let's do this one. So what we have now would be something like this. So phi of 0, phi 0, and then we have an I dagger, A. We have the reference term. And this is multiplied, sorry. Aj of phi 0. So this is the vacuum state. And now we see that the contractions which we can make here, since now A is different from B by definition. So these are 2 different Slater determinants. They're still of the 1 particle, 1 hole type. So we have simply, this is a definition we have made here. We looked at the diagonal earlier, right? But now we have decided that these are different 1 particle, 1 hole Slater determinants. So then you see that the contraction I could make with the particle states is this one and that one. And they are both 0. So the first term is 0. I'll just put that one to 0. Now let's go to the next one. And now we stay with this a little bit sloppy approach where we skip the different terms, but we only look at the contractions. And you will see that's pretty common in many textbooks because else you carry with you all these constants. So what we would have then would be an AI dagger, AA, and now we have an AP dagger of AQ, and then we have an AB dagger of AJ, multiplied with a vacuum state here. So let's take a look at this one. Now here, obviously, a contraction which is viable is this one. And then I can take this one as well. And that means that I'm left with that one. And we see immediately that one has to be 0, right? Because I and J cannot be the same. So this is 0. So let's look at another possibility. So what I could do now is to let AI go to Q here. And then I could let the P go to J. That is also non-zero. But then I'm left with AI with AB, which is 0. So this requires delta A and B. All the other contractions are actually 0 here in this case. Because the other ones would be of the type where I now connect AA with AQ, AP with AB. I would try to connect that one with that one, which is 0. I could connect this one with this one, which would be 0, and so on. So this is also a term which is equal to 0. So the one body operator gives me 0 because the single particle states are different here. So let's now look at let's just continue a little bit because now we are getting all these contributions which are 0. So the only thing now which we could think of is actually something which would come from the two-body operator. So the one-body operator and the reference state gives us 0. This follows also what we did in the first exercise, in the second exercise set, when we looked at these matrix elements. So let's now look at the second term. So we would have a phi 0, or the third term actually, interaction. And then I have my AI dagger AA, and then I have my AP dagger AQ AS AR, and AB dagger and AJ on phi 0. So let's go through the all the possible contractions here and look at what we can get. So one contraction, which is pretty obvious, is actually this one with that one. That's something we could contract. And then we could now also contract AI with AS here. We could contract AA with this one. And finally, we could actually contract this one with that one. So these are operations which actually are non-zero. So I will get a Kronecker delta now, which says delta I, and then S. I have a delta A and P. I'm going to get a delta Q with a J. And then finally, I'm going to have a delta R with B. So this is going to give a matrix element, which now looks like as follows. So I have A and P, which is different from 0. I have R and B here, which is different from 0. So that means that one of the, I would get the following matrix element. I would get an A. And then I have a state here now where I have if you look at the state with Q here, so Q is contracted with J. So I have J here. I have a V here. And then I look at my state I, that's contracted with the S. And then the state Q is contracted with, sorry, the state, state Q is actually, no, not state A, state R is contracted with B. So this gives me B, and then I'm going to have, oops, pen is low here, okay. And then this is contracted with I here, like that. Now, for this specific matrix element which we have, you're also going to see that now there's a crossing line here, as you can see. And that crossing line here and here, that's going to give rise to a minus sign here. And now what I can do now is actually to continue, and there will be 3 more contractions, which are going to give something which is non-zero. And I'm actually going to leave that as a small exercise to everybody here. So plus 3 more, and this is, I was thinking actually of stopping here now. So 3 more contractions. And when I bring everything together, this set of matrix elements, which we're going to get now, they are actually, when we use the properties of the anti-symmetrized matrix elements, I'm going to get matrix elements of the type of AJ. Again, I get 4 of these matrix elements, and it's going to be V, and I'm going to have I and B, like that. And this is going to be anti-symmetrized. So I'm going to leave that as a small exercise, show this. And then finally, the final challenge for the weekend is actually to calculate this matrix element here, IA, and then we have a state, an operator, the same operator, and then we have a two-particle two-hole state, where I have J and K, and I have B and C, and these are different from the single particle states which we have to the left. So this is a little bit more involved. And if you go to the textbook of Shavit and Bartlett, You will see this developed in chapter or in section 3.8. Okay, so it fits actually to stop a little bit earlier, essentially because now we have many of the ingredients which we will need next week. And next week, we're also going to bring up a diagram, a further diagrammatic representation of these terms. But the first thing we will start with next week is actually to discuss full configuration interaction theory. So that's going to be the first real many-body method which we need. And all the ingredients which you see here, these are ingredients which we will need next week when we are setting up the matrix to be diagonalized. And we are going to apply these kind of things to the Lipkin model as our test case. Okay, I'm going to stop the recording here. And so let's